Hey, welcome back. This is 6.4, and what's going to happen here is we're going to get another mathematical model, this time being a little bit more realistic than what we saw with the exponential growth model. Okay, in particular, there's this thing called a limiting capacity that kind of keeps the population from just getting humongous, right? So we'll begin with the definition. So the logistic differential equation looks like this. The rate of change of the population, and it kind of starts out just like the exponential growth. Okay, so in that regards, it has that factor in it, the k times y. If you solve this, you would get, y equals ce to the kt, right? But then they're going to put in this other factor which can limit the growth, 1 minus y over L, okay, where L is this thing called a limiting capacity or a carrying capacity, or whatever they want to call it. So see what happens when, let's say, for example, L is 100, right? So our differential equation, dy over dt, will be k times, well, I lost my y there, and then 1 minus y over 100. So what does this limiting capacity do? So when the population is greater than 100, so when y goes over 100, the differential equation will, assuming k is positive, okay, k is greater than 0, L is also going to be greater than 0. Assuming k is positive, what you end up with is a rate of growth that's negative, right? Because you're going to have 1 minus something like 103 over 100, and this factor here will be negative. That's less than 0. So the overall rate of growth, which is the change in population or whatever you're looking at, is going to be negative. The population is going to be decreasing. So, if you start with 40 animals, or if you start with 103 animals, sorry, I'm trying to draw a little animal here. I don't know, looks like a bug. The rate of change is going to be it'll be negative. So you're going to end up, maybe going down to 100 of these bugs. Okay. Then if the population growth, if the population goes like less than 100, it's going to be a growth, because that factor will be then, it'll be positive, ky times 1 minus like 50 over 100. This factor here will be greater than 0. And of course, your little bug animals will have a growth rate which is positive, so an upward slope, in other words. So maybe I have 50. I think the only reason why I'm doing this is so I can draw the animals, honestly. And then it's going to maybe go, who knows, up to 75, right? Okay, so that's why it's different than the exponential growth. It's more realistic. We want to go ahead and solve this to get the logistic equation. So this is the logistic differential equation. We want the logistic equation, right? So I'm going to use separation of variables, and there's a little extra stuff we have to do that we don't know how to do yet, but we'll learn how to do it later, that I'm going to talk a little bit about. So first I'm going to rewrite it by factoring out a 1 over L. So I get ky over L times, this will end up being L minus y. So I just factored 1 over L out. You can see if I redistributed 1 over L, I'd get 1 minus y over L. Then I'm going to separate, so I'm going to leave dy over here, and what do I end up with? I'll have, how do I want to do this? I want to get everything except the k over, so I'll have L over y times L minus y dy, and over on the other side I'll just have k dt. Okay. To integrate on the left, that's where we're going to have to do something that we don't know how to do yet. And you're not going to be expected to do this, but we'll learn it. It's called partial fraction decomposition. And basically what that means is you're taking one fraction, this thing, the L over Y times L minus Y. You take that thing and you turn it into two fractions. It's the reverse of finding a common denominator. Okay. So if you go through, once you learn how to do it, it'll turn that fraction into this sum of fractions. And you could, if you wanted to, prove it to yourself that that works just by finding a common denominator, and it'll end up back there where we started. Okay, but we'll learn how to do that in the next chapter, I think. On the other side, we have KET. Okay, and then we can integrate both of these, so they're natural logs. So the first one is ln absolute value y. The second one, you'll have to do a u sub, and you'd end up with a negative kind of floating about u for L minus y, and then du is negative dy. So you're going to end up with a negative ln absolute value of L minus y. And on the other side, you'll have kt plus c. Okay, I want to get an explicit solution, so I'm going to use the rules of logarithms to rewrite this difference as a log of a quotient. So I'm y over L minus y. And then I'm going to exponentiate both sides. Okay, so I'm going to end up with absolute value of y all over L minus y, and that'll equal e to the c times e to the kt. And then I am dropping the absolute values, replacing with a plus or minus, and then replace that just with a big constant c. Then I want to multiply both sides by L minus y. Okay, so times L minus y. So I want to get y equals something. So I'm looking for an explicit solution. I'm going to distribute this. I'll have CL e to the kt minus y e to the kt. Move the y e to the kt to the other side. So I'll have y plus y e to the kt equals CL e to the kt. Factor out the y. Let's move back over here. You get 1 plus e to the kt equals CL e to the kt. Did I lose a c somewhere? Yeah, I lost a c on this. Okay, so c has to be on u. Sorry about that. And then there's going to be a c on that guy. Divide both sides, so I get CL e to the kt all over 1 plus c e to the kt, which is an explicit form, but we want the form they have in the book and the formula that's traditionally viewed as the logistic equation. So I'm going to divide or multiply both sides by e to the divide both sides by divide top and bottom by c e to the kt. Okay, so I guess multiply by 1 over that. 1 all over c e to the kt. That'll give me up top just L. On the bottom, I'll have 1 all over c e to the kt plus 1. And then what we're going to do is rewrite that as, first I'm going to use the commutative law of addition to rewrite it as 1 plus the 1 over c e to the kt. This thing is also written as 1 over c e to the negative kt, and then I'm going to replace this 1 over c with a constant we'll call b. Okay, so we'll end up with 1 plus b e to the negative kt, and this is the form of the logistic equation that they give in the book. Okay, so this is the logistic equation. And again, once you have the hands on the logistic equation after doing this differential equation, then you could kind of just forget about it, right? So here's our you can kind of forget about the process of solving for the equation. So there's the logistic differential equation, and down here is the logistic equation. And that's what we kind of need from this sort of explanation here. Okay, so one thing to note about the logistic equation is that as time goes to infinity, so as t goes to infinity, this thing will go to, y will go to the limiting capacity. You can kind of tell that by taking the limit of the thing. So note the limit of L all over 1 plus b e to the negative kt. If we take t going to infinity, this bottom part where you have the b e to the negative kt, that part will end up being 0, and you're just left with L, right? So if you consider, the limit of b e to the negative kt, that's the same as the limit of b all over e to the positive kt as t goes to infinity, and k is positive, t goes to infinity. And so, in the denominator, you're going to have like e to the 10, e to the 100, e to the 1,000, something huge, right? So it's going to be form L over infinity, and those forms always end up being 0. Okay, so that part is going to zip off to 0, and you're just left with L over 1, in other words, L. Okay. So over time, your population will tend towards this limiting capacity. If you draw the thing, it's going to look like something like this. Here is the limiting capacity L, and in between 0 and the limiting capacity, you'll have sort of this beginning as an exponential, but then kind of curving over. It has an inflection point in the middle, and becomes concave down, and then heads off towards L in the negative direction. If you go above L, there's of course this kind of reversing scenario where the population is decreasing until it levels off down to the limiting capacity. Okay. Okie dokie. Let's look at verifying this thing as a solution. This is kind of a weird problem. I wouldn't ask you to do this, but verify the equation. I just want to show you for the sake of showing you, and there are problems in the book, but I don't think there's one on WebAssign where you have to do this. But it's not a bad thing to see, so let's take a look. Verify the equation satisfies the logistic differential equation. I'll just abbreviate and write DiffEq. So this, let's see what it is. I'll just call it an example. The differential equation, of course, dy over dt equals k times y. Ugh, get my eraser here. K times y times 1 minus y over L. And then we're trying to check if this thing, this logistic equation, satisfies it. Okay, we kind of did this in the beginning in 6.1, just making sure our solutions satisfy differential equations. We could rewrite this. Well, one thing to note: the L value is 12. The K value seems to be just 1. It's always e to the negative kt. So negative kt is equal to negative t in this case. So k is 1. You could rewrite it so I have to take the derivative because I need the derivative in order to figure out whether or not it works. So this is 1 plus 6e to the negative t to the negative 1. Take the derivative, so that's a power rule with a chain rule. Bring down the negative 1, I get negative 12 times 1 plus 6e to the negative t to the negative 2 times, it should be a 6, it'll end up being negative 6e to the negative t, right? So the derivative of e to the negative t is e to the negative t times negative 1, and that's where you're getting your negative 1. Okay. Okay, I think that'll get us through the show. Let's go ahead and then we'll start on the left-hand side. So starting on the left-hand side, we note the dy over dt equals, and now I use my given information, the derivative and the equation that I'm checking to kind of fill in the gaps here. So the derivative is sitting right here, so I borrow that, negative 12 times 1 plus 6e to the negative t. So negative 2 times negative 6e to the negative t. Then I have some fancy algebra footwork to do, and this is the part where it gets kind of weird. So I keep my goal in mind. I got to get it into this form. Okay. So I'm going to rewrite this first part and a little bit of the second part in a weird sort of way. First, I note negative times negative is positive, and I want a y value, right? So the k is just 1, so I don't have to worry about that. So I want to factor out the y part of it. So the y part is 12 all over 1 plus 6e to the negative t. Okay. And then what's left over, right? So there's a factor of 6e to the negative t, and then there's also a factor of 1 plus 6e to the negative t. Okay. So hopefully you could kind of back engineer this expression from this expression if you don't believe that these two are equivalent. Okay, it's just a complete rearranging of that stuff. And again, the reason why I'm doing that is because that first term now is the y that I want in my logistic differential equation, right? So from my given information, that's this guy right here. And now I could replace that with y, right? So I have y times this other thing. And this other thing I need to rewrite as a difference. And you can do long division in order to pull that off, but it's a little easier to pull this trick where you add and subtract 1, right? So you have 6e to the negative t plus 1 minus 1. And then you could split it up into two fractions. Okay, so you're going to have one fraction here, which will just give you the 1 right here. And then you'll have another fraction here, which you might have to do a little bit of work to get it into this form of y over L. Okay. Okay. So what do we have then? Y times the 6e to the negative t plus 1 over 1 plus 6e to the negative t. That's just 1. And then minus this 1 all over 1 plus 6e to the negative t, which I'm hoping to rewrite as y over L. Okay. So I could get the L part if I just multiply in 12 over 12, right? So that's what I'm going to do. It doesn't change anything because 12 over 12 is the same as 1. And then I could rearrange it by just kind of pushing the 12 over into the numerator here, right? And then that's going to be y, and the 1/12 is 1 over L. Okay, so I end up with y times 1 minus 1 over 12 times 1 all over 1 plus 6e to the negative t, which is y times 1 minus, whoops, this is a 12 up here, 1 over 12 times y, which is y over 12, which is y over L, which is the logistic differential, the right-hand part of that logistic differential equation, of course with L equaling 12. Okay. So that pretty much does it. That verifies it. And like I said, it's a little tricky algebra and kind of creative thinking, but it gets there. So this, which is the right-hand side of the differential equation, the diff EQ, which is what we wanted to show. Okay, so it works. Great. Let's look at another one. So in this problem, they're giving us a differential equation. They want us to find the k value, the L value, and determine the p value where the population growth is the greatest. Okay. So the differential equation they're giving us, the rate of change of p with respect to t is equal to 0.1 p minus 0.0004 p squared. I want to put it in the form of the logistic differential equations so I could figure out, part A here, what is the K value. Okay, so I'll do some factoring. I'll factor out a 0.1p, so it looks like K is 0.1. Okay, so I'll have 1 minus 0.004 times p, and clearly, the form is K times Y times 1 minus Y over L, right? Okay, so K is equal to 0.1. For B, find L. I should be able to then use this to determine L, right? So I note that 0.004 is the same as 4 1,000ths. So this thing can be rewritten as 4 1,000ths p, or 4p over 1,000. And of course that's just p over 250 if you simplify. So the L must be 250. Determine the p-value where the growth is the greatest. So if you're working with fruit flies or something, this would be the population such that the population size such that the people in the population, or in this case the flies in the population, are producing the most babies. So determine the p-value where the growth rate is the greatest. Okay, and if you think about maximizing and minimizing from Calc 1, what did you have to do? You had to take the derivative, right, and then set it equal to 0 and get the critical points. Here we want to maximize the growth rate. So what we're going to need to do is take the derivative of the derivative. Okay? In other words, what you're looking for here is the inflection point. Okay, so we begin with our differential equation, which is basically the first derivative. And then we take its derivative. So I give us a second derivative. And what do we have then? So it's kind of like implicit differentiation. I have 0.1 times 1 p prime, so 0.1 times p prime, minus, doing a power rule here, 0.0008 times p prime. Okay. Then I'm going to rewrite it a little bit so it's easier to set equal to 0 and solve. So we'll have 1 minus 0.008 p, okay, and then we set it equal to 0 and get the inflection points, if there are points. This part, the p prime part, that will equal 0 exactly where this thing equaled 0, back up here, wherever I guess, where are you? It's right here, right? And that equals 0 when 0.1 p equals 0, which is when p equals 0. In other words, this is kind of a steady state, right? When the population is 0, there's no growth rate. The growth rate is 0 as well. And then when the so the other one is when 1 minus 0.004 p is equal to 0. And if you solve that, what do you get? You're going to get 250, right? 0.004 p equals 1. Multiply both sides by 4 1,000ths, you get 1,000 over 4, which is 250. Which is the other kind of equilibrium solution. So when your population is exactly 250, it's going to stay at 250, okay? Because our curve kind of looks like this. And then you have kind of a solution here, a trivial solution at 0, and a trivial solution at 250. If you remember us from the last video, we talked about trivial solutions. So if you find p-values where the function in terms of p is equal to 0, those are trivial solutions, and that's what you have there, the 0 and 250. There's no change at those places. The rate of change of p will be 0. So anyways, what I'm getting at is to disregard this part. Just sort of throw it out and focus all your energy on that second factor, this guy right here. So set that equal to 0, long story short, and solve for p. So you get 0.008p is 1. Multiply both sides by 8/1000ths, so you end up with 1,000 over 8, which is, I think, 125, right? Okay, so the population is growing the greatest at 125. Anybody notice what that number is? That's just half the limiting capacity, L, right? L is 250. P is 125, and that will always be the case. So if you just go through it in general, you'll determine that to work in that way. It turns out the population is growing the fastest when the population is at L over 2 or half the limiting capacity. One way to think of it is terms of zombies. If every other person is a zombie, that's when you don't want to go outside, okay? Similarly, if every other person has COVID, that's when you don't want to go to the grocery store. In the beginning, you probably could have gotten away with it, but as time goes on, no. So right now, I don't go out anywhere. I stay at home. I have my groceries delivered. My mom is 78 and she smokes, so I don't mess around. Okay, let's look at an application. So this one I think is in terms of panthers. But if you'd rather, you can think about zombies. Okay, so application example. So let's say we have an island of 200 residents, 200 people, has an outbreak of zombies. Basically, a government plane crashes and it's carrying this virus that turns people into zombies, and when it crashes, 25 people go to the scene and they all get infected. So in the beginning, there are 25 people infected. Okay. And then there's a scientist on the island, and he's very worried, and he looks after 2 days. He noted that there were 14 new people infected. We want to get a logistic equation, and then a logistic differential equation, and we want to see how many people are going to be infected after 5 days, and we're going to use Euler's method to crank out a solution and determine when it's going to be the worst. When do you not want to go out? Of course, with the zombification, the more people that are zombies, you know, it's like obviously the rate of change is going to slow down because there's everybody's a zombie, you know, after a period of time. That doesn't mean you want to go outside. It just means the rate of change is going to slow down. So anyways, let's go ahead and take a look here. Part A, find the logistic equation. And we'll start out with our sort of template model, y equals L all over 1 plus e, and it is negative kt. So it's a little different than like your exponential growth equation where it's always ce to the positive kt. Okay, so L is given as 200 people. That's, you know, there's only 200 people on the island, and we'll assume they're all sterile, so they're not having kids or anything. That's why they're on the island for some reason. Okay, so what else? In the beginning, there's 25 zombies, so at time 0, there's 25 zombies. After 2 days, there's 14 new infections, so at 2, it'll be 39 people infected. Right, so we should be able to use this information to get L and K. Obviously, we have L, it's 200. I need to get K now, so I use, let's use 0, 20. Well, I lost the B value, right? So there's actually 3 variables we need to figure out, the L, B, and K. I have the L, I need to get B and K now. So I'll use the initial condition, 25 zombies. B, e to the 0 is just 1, so it's 1 plus b. Multiply both sides by 1 plus b, divide both sides by 25, 8, subtract the 1 over 7. So our model now, y equals 200 over 1 plus 7 e to the negative kt. Then I need to get k, so I use the next initial, so I use this one, now I use this one. So I have 39 equals 200 all over 1 plus 7 e to the negative 2k. Again, kind of cross multiply. Move the 1 over. So it'll be 239ths minus 3939ths, which is like 16139ths. Divide both sides by 7. So that'll go into the numerator 23 times, all over 39. Take ln on both sides. So you're going to end up with negative 2k equaling ln of 23 over 39. Divide both sides by negative 2, and you have your growth constant. And then we have our final logistic equation, y equaling 200 all over 1 plus 7 e to the negative, which will be positive, 23 all over 39 all over 2t. Okay. Okay. Part B, how many zombies are you going to have after 5 days? So if you plug 5 into there in your calculator, you're going to get about 70 zombies. Part C, they want to know when is the rate of change of the zombies going to be the greatest. And again, from above, you can just presume that that will happen when the population Y is equal to half the limiting population, so 100. Okay, and so you're just going to solve for t in the logistic equation that we made in part A. So 100 equals 200 all over. So what are we doing? We're looking for for when you basically do not want to be on the island, for when the zombification is the greatest. Right, so 200 all over 1 plus 7e to the, whatever the k was, negative k. And then we're going to solve for t. So bring the 1 plus 7e to the negative kt over here, equals 200 divided by 100 is just 2. Move the 1 over, so I get 7e to the negative kt equals 1, divide by 7. 1/7, natural log on both sides, and now I'll write the k back in. So I have ln of 23/39 all over, the heck was it, 2. T equals ln of 1/7, and then multiply by the reciprocal of ln 23/39 over 2. That'll give me 2 times ln of 1/7 divided by ln of 23/39. And if you put that in your calculator, you're going to get about 7.37 days. Just a week in, you're going to be in a real world of hurt. Okay. Part D, they want you to use Euler's method to get an approximation instead of part B. So part D, use Euler's method to determine or to estimate a population on day 5. So it's basically you're just redoing part B. Okay. So the quiz, figure out how many zombies you're gonna have after let's say 100 days. Okay. No, let's just say 10 days. Let's not get carried away. Okay, so that's the quiz. Let me mark that down in my notes here before I get too carried away. 6.3. So how's everybody doing? You surviving? Getting through the pandemic? 6.4. I need to figure out y of 10 for the zombie problem. You could just use the logistic equation to figure that out. You don't have to do Euler's method. Okay. But anyways, in this problem, we're going to do Euler method on a line. There, you will have to do that as well in WebAssign. So, anyways, we need to produce the differential equation that will give us kind of these changes in y's that we need for Euler's formula. So anyways, dy over dt is always k times y times 1 minus y over L. In our case, our k value then would have been negative. So you got to be careful with that stupid negative thing. Negative ln of 23/39 all over 2 times y times 1 minus y over 200. Okay, so our Euler method, so you're going to start with x sub 0 is going to be, we want to do it in terms of like a general thing, right? They want you to use an h value of 1, which is pretty unrealistic. It's going to give you probably not a good answer, but we'll try it. The h value is 1. Then our formula for y sub n is going to be y sub n minus 1 plus h, which is 1, times dy over dt, basically, right? So that's going to be negative ln of 23 over 39 all over 2 times y times 1 minus y over 200. So it's a real nightmare, as you're kind of noting, I'm sure. Carried away with the parentheses. And of course, x sub n is just going to be x sub n minus 1 plus 1, the h value. Okay, but let's go ahead and just use the internet to figure this out, right? Let's zip on to the Euler Method calculator here. So I'm going to plug in my differential equation, negative ln of 23 over 39 times y. So y times 1 minus y over 200. The initial x value is 0, of course. The initial y, we said there were 25 people. 25 zombies. Yeah, 25. We want to know how many zombies after 5 days. The step size we want to be 1. And we're not going to type in the exact solution. Let's not bother. Right? Oh, we could get extra decimal points if you want. Okay, that's cool. Sure. I'm getting some crazy number. What did I do wrong? It should be plus in here. Because you know it's supposed to be around 70 zombies from part B. Still screwy. What did I do? 23 over 39. Oh, it should be over 2. I lost my divided by 2. Calculate. Still off. Geez, I just tons of errors. I don't know what my problem is. It should be minus. It is minus. Sorry. Hopefully that does it. That's better. So 65, it's still pretty far off, but it's because our step size is so big. Probably if you did a different step size. So I'm saying my approximate answer is 65.565 for y of 5. Is approximately 65.565 to 3 decimals, 65 zombies. And I'm sure if you increase that step size or decrease the step size, you get a better approximation, right? So let's not bother. Part D, actually that was part D, wasn't it? Yeah, part D. Part E then is to determine when we already did this, determine when the growth rate is maximum. That's just going to be 7.37 days. We kind of already did that up here. Okay, so we'll leave it at that. I think that'll be good enough to get you through the homework online and WebAssign. And we'll leave it at that for you today. Okay, so thank you for watching as usual, and we'll see you next time.